Welcome. Greetings to everyone who is watching this video. Myself Natarajan, me and my teammates Lalith, charan and Sanjeev Kumar had done a project for my final year Viva project examination. The title of the project is Design of Wideband Directional Coupler using SAW technique for X-band application. This project is guided by our very own staff, Mr.Ruban, who is an assistant professor at EC department, Veltech Multitech. Before getting into the project, first we must know what is SAW technique. SAW technique is nothing but substrate integrated waveguide technique, which is moreover similar to the rectangular waveguide technique. But the design of this technique is similar to planar waveguide technique. We all know that rectangular waveguide has very much good advantages when compared to the planar waveguide. But the design of rectangular waveguide is very much difficult when compared to planar waveguide due to its rigid and three-dimensional structure. In this technique, we can able to design a planar waveguide which is much more similar to the rectangular waveguide. So let's get into the project and we will see how it works. The design is made at HFSS, which is nothing but high frequency structure simulator software. Here, the software is used to find the measurements of the equipment which we are going to design for the users. Initially, the substrate is taken in this project. The substrate we are going to use here is Arlon 1000. Next, the ground plate, which is the copper plate. After that, we wanna insert the via holes, which is nothing but the pin circle shown in the diagram, which is the via holes, which is used to propagate the waveguides. After inserting the n number of via holes in the substrate, we are getting like this. It should be copied and pasted in the other sides also. After that, we gonna get like this. This is the final via holes propagation methodology. After inserting the via holes, we are going to set the aperture. Aperture is the one which decides the measurement purposes for the other equipments, which is the main thing we gonna see here. By changing the aperture angle, we can able to change the measurements what we have to need. In this substrate, we are setting the aperture to the center of the substrate. This is the three-dimensional view of the via holes we have set in the substrate. After setting this, and we have set the aperture. After the aperture setup, we go for the port insertion. There are 4 ports in the directional coupler: port 1, port 2, port 3 and port 4. Port 4 is an isolated port. Initially, 2 ports are set up, port 1 and port 2. Port 1 is an input port, port 2 is an through port. After that, 4 ports are set up. Port 3 is an isolated port and port 4 is an ideal port. By designing process, by theoretically port 4 is an ideal port, there is no loss. But by doing it practically, we have some minor losses at the port 4. After the 4 port setup, we have to keep it in the radiation box. The radiation box is much more similar to the anechoic chamber. Here the radiations are passed to the ports and the measurements have been made. This picture is nothing but the electric field distribution of the 4-port network, which is the directional coupler electric field distribution picture. This is the graph we have obtained after kept it in the radiation box. These are the 4-port network graph. By this, we can able to find the S matrix value, which is applied at the theoretical values of the directional coupler. The 4 S values are converted into input power, output power, back power and forward power. By using these power values, we can able to find the measurements such as directivity, coupling factor, isolation loss and return loss. These are the factors we are going to measure using this SAW technique directional coupler. After finding these values, we have obtained these final outputs. In this table, we can able to find the traditional and the proposed system are almost similar when compared to planar waveguide. In this, we designed a planar waveguide using SAW technique, but the result we have obtained is much more similar to the rectangular waveguide. So we can be used to any other RF applications for this using this waveguide technique. Nowadays, most of the RF and the microwave applications are using the rectangular waveguide technique, but the design process is much more difficult. So we have designed a scalar waveguide which acts as a rectangular waveguide technique. So this can be applied anywhere instead of rectangular waveguide on any other applications. These are some of the applications which the SAW technique can be used. communication, radio astronomy, defense and the radar communication, space and navigation, positioning measurements. These cases we can replace the rectangular waveguide instead of SAW waveguide technology. Okay, these are the reference papers we have gone through in the IEEE sections. Thank you.